This is Algebra 2 with Trig 2.9a, finding the probabilities of compound events. But first we're going to start out with some probability with factoring questions. So as I've shown you this exact problem before, 6 times 10 is one way that we can help factor this problem. If we use a method called factor by grouping, we're taking the A term and the C term and multiplying those two together. I like to make a table with those values. Some people like to make an X and then they visually try to figure out, mentally try to figure out what multiplies to be negative 60 and adds to be negative 7. If you can figure out those numbers right away, you're doing awesome. If you're not sure, you want to think about, to multiply to be a negative, your two signs have to be different. So I like to write the plus and minus above there. For them to add to be negative 7, that means the larger number has to be negative. And you may realize that that's going to be a positive 5 and a negative 12. That's going to multiply to be negative 60 and add to be negative 7. So we bring down our 6x squared, our positive 5x, negative 12x, and bring over your negative 10. Then we're just using our factor by grouping skills. Remember what we've talked about before. If you're good with guess and check, that's wonderful. We'd love you to use guess and check. But if you have troubles coming up with the values, we don't want to sit there for 3, 4, 5 minutes trying to guess and check your way to it. What factors out of your 12 and the 10? But a 2. 2 times 6 gives me 12. 2 times 5 gives me 10. It has to be a positive 5, negative 2, positive 5 gives me negative 10. Notice my parentheses are exactly the same. So we're all done. X minus 2 and 6x plus 5. And that's factored. You can always check your work by foiling this back together. So go ahead and use that method here for the second one. I'll pause the video, and when you get done, turn it on. We'll walk you through it. With this one, we can talk about it as a guess and check format. If you want to use factor by grouping, you would say 9 times 8 is 72. What adds to be 6? You could go through your factors. That would work great. But we can also talk about it as a guess and check. What multiplies to be 9? Well, 3 and 3 is pretty common. So I would suggest, I would always start with 3x and 3x, because together they make 9x squared. If I use that theory here, I probably would have used 2 and 3 in this case. I would have started with 2 and 3 with guess and check. And it wouldn't have worked out. I would never have gotten the answer. So sometimes when you guess and it doesn't work out, it just slows you down. So not always a great method to use. But if 3 and 3 make 9, now we need to come up with two numbers that multiply to be 8. And that's, of course, going to be 4 and 2, or that's going to be 8 and 1. We've got to figure out which is going to be best to use. We want to get close to 6. So if we did 3 times 4, that would make 12. And 2 times 3, that would make 6. So 12 and 6 can make 6. If it was a positive 12 and a negative 6, then we just added to become 6. And there's our factoring. We're done. So sometimes factor by grouping can be good. If you don't prefer factor by grouping, you can always use, this is guess and check, sorry. We can use factor by grouping. We're going to move on to compound events. Probability of compound events. When you consider all the outcomes for either two events, A and B, you form the union. So this is an example of union. We're taking all the events of A and all the events of B. When you consider only the outcomes that are shared between the two, that's the intersection. The union or the intersection of two events is called a compound event. So if we have two situations, A and B, maybe A is a soccer player and B is a baseball player. So you have soccer players that are also baseball players. And they fall in the Venn diagram here in the center. That can be illustrated by the dots that are the same in both. You could possibly have soccer players on a team and baseball players on a team that don't overlap. Or maybe you could use two fifth-hour classes. You're either in this fifth-hour class or you're in that fifth-hour class. You're not in the same classes. They don't overlap. Classes don't typically overlap. So that would be an example where they're completely empty in terms of their overlap. So to find the probability of A or B, you must consider the outcomes, if any, in A and B, if there's any overlap. These events are called overlapping. If they have one or two outcomes in common, one or more outcomes in common, then they're going to be represented here. That has overlapping. Two events that are disjoint or mutually exclusive, they mean the same thing, mutually exclusive or the word disjoint. They have no outcomes in common. So that would be our third box. This here is an example of disjoint. You might want to label that on your notes. That's what disjoint is. That's where they are completely separate events. So we have two different formulas we're going to use. If A and B are any two overlapping events, then the probability of A or B is the probability of A plus the probability of B minus the probability of their overlap, A and B, because that's where they're the same. Let's come on back up here to our diagram. If you look at and you count all the dots that are in A, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you count all the dots that are in B, 1, 2, 3, 4, 5, 6, 7, 8, you got 9 and 8, that's 17. But there aren't 17 dots here. But I clearly counted 17. There's 9 in A, and there are 8 in B. That's because you counted a portion of them twice. So you don't want to count that repeated time. So we get rid of the overlap ones. You're not getting rid of all the overlaps. You're just getting rid of that calculation one time. In event A and B, if they're disjoint, if they don't have any overlap, then it's simply the probability of A plus the probability of B. There is no subtracting the overlap because there is no overlap. So you need to know, is there overlapping or is it disjoint? What's the topic covering? You got to get yourself invested in the question. So when we flip the page over, I look here just right away and I see that A and B have overlap. They overlap 25% of the time. They're not disjoint because there's overlapping. We're going to use the probability of A or B to equal the probability of A plus the probability of B minus the overlapping of A and B. So the probability of A is 0.6. So we plug that in for the probability of A. 0.32 is the probability of B. I don't know what the probability of A or B is, but I do know that the probability of A and B is 0.25. So this becomes 0.92 minus 0.25, and that's going to be 0.67. So that's the probability that A will occur or B will occur. So we can come on over here and just do it again. In this case, we don't know if there's overlap. It's still the same formula. We won't change the formula on you. We'll take the probability of A. Well, actually, we'll take the probability of A or B to equal the probability of A plus the probability of B minus the probability of A and B. So we're using the same formula we did here. Just didn't rewrite all the words again. This is the OR. This is A. This is B. This is A and B. That's the part we don't know. So we get 0.5. We add these two together. 0.2 and 0.4 is 0.6. Then there's a 5 minus the probability of A and B. Subtract 0.65. And that gives us negative 0.15 to be equal to negative the probability of A and B. So by dividing by your negative, you see that your overlap is 15% of the time. It's 0.15. That is disjoint. Not disjoint. That is not disjoint because we have a spot where they are overlapping. This is an example of not disjoint, just like we said over here. So it is overlapping. So this is a pair. This is where you get to work with your partner next to you. If you're at home, give it the best shot you got. Pause the video, and we'll come back and talk it out. So here we're looking at drawing one card from a standard deck of 52. We have two different situations going on. Event A is drawing a king. Event B is drawing a red queen. So the probability of drawing a king would be, there are 4 of them out of your 52. If you would like to turn your page over and look at the chart of cards, you can easily do that, and you see that there are 4 kings, 1 for each suit. So that kind of justifies how this can be reduced down to 1 out of 13. The probability of B occurring. Well, event B is drawing a red queen. Look back at your chart. You'll see that there's 2 red queens, a diamond and a heart, out of the 52 cards. So that's going to be 1 out of 26. Now, what would be the probability of drawing a king or a red queen? Well, the probability of a king is 4 out of 52. The probability of a red queen was 2 out of 52. So we add those 2 together, and we get 6 out of 52. Well, did we count any of the same cards twice? If you need to look back at your chart, I counted 4 kings in the last column, and I counted 2 queens that were both red in the second to last column. I did not count any of the same cards twice. You cannot be a king that is also a red queen, so there is no overlap. So the overlap is 0. So this topic is disjoint. The other 2 examples up here were not disjoint because they had overlap. Here we calculated what it was. Here they told us in the beginning that there was overlap. It was not disjoint. In this situation, we got disjoint because you could not be a red queen that was also a king. That does not mean that a standard deck of cards is always disjoint, because you can have topics that might overlap. You might have the probability of drawing a king and probability of drawing a red card. There you're going to overlap. Here we're rolling a 6-sided die. What's the probability of rolling a 2 or a 5? Probability of 2 or a 5. That's the probability of a 2 plus the probability of a 5. Now, do I have to be concerned about a 2 that is a 5? Can you be both? No, of course not. So we're not subtracting anything. So we have 1 out of 6 plus 1 out of 6, which is 2 out of 6, which is reduced to 1/3. That's a probability of a 2 or a 5. How about the probability of rolling an odd number or rolling a multiple of 3? So, probability of odd or multiple of 3, I'll just use M3, is going to equal the probability of odd plus the probability of M3, multiple of 3, minus, if there's any overlapping, where odd and M3 occur. So what numbers are odd?
3, 1, 5.
1, 3, and 5. Those numbers are odd. What numbers are considered multiples of 3? So the probability of an odd number was 3 out of the 6 possible numbers. The probability of a multiple of 3 was 2 out of the 6 numbers. And was there any overlap? Was there any numbers that were used in both situations? So that was 1 of the 6 numbers were the same. So we get 5 over 6 minus 1 over 6 gives us 4 over 6, which can be reduced to 2/3.
Do you not want the decimals for these ones?
A card is randomly selected from a standard deck of 52. What's the probability that it is a face card or a spade? Well, these are all the face cards. These are all the spades. If you go back and look at your list, you should have grouped these all together, which were the different face cards. The spades are all these 13 cards. And you notice that you're counting some cards twice. So, probability of a face or of a spade is going to be the probability of a face plus the probability of a spade minus the probability of a face card and a spade, a face card that is a spade. So what's the probability of a face card? 12 out of 52. What's the probability of a spade? 13 out of 52. And how many face cards are actually spades? How many of these cards did we count twice? 3 out of the 52. The Venn diagram supports this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There were 12 out of the 52 total cards in a standard deck. Of just the spades, there are 13 of them here. How many of them are overlapping? It would be 3 of them. So this makes 22 out of 52, which can be reduced to 11 out of 26. Now this can often be a little tricky because there's so many words. Just pay attention to what the words are. Of 100 students that are surveyed, 92 either own a car or a computer. That's your or situation. You have 92 out of 100 are or. 65 of the 100 definitely own a car. 82 out of the 100 definitely own a computer. But what's the probability that you own a car and a computer? So we've got probability of a car or computer. And that's the probability of a car plus the probability of a computer minus the ones that have a car and a computer, because you've just counted them twice. 92 out of the 100 own a car or computer. 65 out of 100 at least own a car. 82 at least own a computer. And we're trying to calculate how many own a car and a computer. Because mathematically, it's got to match up. It's got to calculate out. So we have 92 out of 100. Here we have 147 out of 100. So we're going to subtract the 147. And that gives us 55 out of 100. It's actually be a negative 55 because you're subtracting a larger number. To be negative probability of a car and computer. And when you divide the negative out of it, you get 55 out of 100. Own a car and computer. And there you have it.